Okay, let's start talking about logistical growth. This first video is just going to be explaining the concept of all this, and then we'll get on to some examples, maybe towards the end of this video, maybe in the next. It depends on how long it takes me. Now, we are used to dealing with, back in Algebra 2 and Pre-Cal, exponential growth. Exponential growth is where you have a population changing with respect to time, and that rate of change is proportional to the size of the population, right? So however fast it's growing depends on how many there are. And we talked about this in terms of bacteria growth and stuff like that. If the population of bacteria in a petri dish are doubling every 6 hours, how many you have after 4 hours depends on how many you had at the beginning, right? Because time, just times 2 doesn't tell you anything. 100 times 2 or 1,000,000 times 2, right? Depending on the original population and the rate of growth. And this is separable. I mean, it winds up being rather easy. And we have k dt, and we can say, well, let's go ahead and integrate both sides, and that's the natural log p is equal to kt plus c. Let's exponentialize both sides, e to the kt plus c, and that winds up being p of t a times e to the kt. Now that ought to look really, really familiar, okay? The exponentials that we actually reasoned out numerically in Algebra 2 and Pre-Cal actually come from a rate of change being proportional, meaning equals at constant times, right? Being proportional to the population. But here's the thing. Most things actually don't act like that in the long term. They may act like that in the short term, but they don't act like that in the long term. And let me give you an example. Let's say, the school that you go to is, let's say, 360 people, okay? Which is, I think, roughly how many people are there. So 360 people are there. Somebody starts a rumor about Susie. Susie is reported to have, I don't know, whatever. Okay, so a rumor starts about Susie. At the beginning, it is going to look like an exponential curve. The rumor is going to spread like wildfire. But as it progresses, what happens is when a person who knows the rumor turns to somebody else and starts to tell it, more and more people already know, okay? And they're like, oh, I already know that. Oh, I already know that. Oh, I've already heard that, okay? And of course, 360 people represents the maximum number of people at the school who can find out about the rumor. Like, if there are 360 people at the school, there is no 361st person to hear the rumor. Okay? So this puts a cap on it, right? It's kind of like, it's like this with the spread of diseases. The spread of diseases sometimes is really, really fast at the beginning, but then it slows down because the infected people don't come in contact with uninfected people. They come in contact with immune or already infected people at some point, and therefore it starts out fast and then it starts to slow down, okay? So whereas an exponential curve looks something like this, right? And it just keeps going on forever. This comes up and looks about the same at the beginning, but then levels off, okay, and starts to hug what's called a carrying capacity, right? Okay, so DVD players, I know you guys are going to be shocked at this. DVD players were not always around, okay? DVD players replaced something called VHS tapes. And you had a VHS player in your house rather than a DVD player. Well, once DVD players start to get popular, okay, you have something like this. It starts out slow, okay, but then people start to realize the convenience, okay, and then it goes up, and let's say that these hash marks represent 20% of the population, 40% of the population, 60% of the population, 80% of the population, 100% of the population, okay. As it goes up, it's going to be a buying frenzy, and then it's going to level off. And the reason it levels off is for the same reason that the rumor leveled off. More than 100% of the population can't own a DVD player. Does that make sense? I mean, it's 100%. It's all of them, 100% of the population is basically the ceiling. It's the cap. It is the end, right, of the growth. So basically, these logistical curves look like this. They start up like this, and if you just sort of look at the beginning, they look like they're going to be exponential. But for whatever reason, whether it's DVD player sales in a population that has a fixed limit, or a rumor spreading, or a pathogen spreading, or the number of rabbits reproducing in an area. Well, the number of rabbits reproducing in an area, won't increase forever, right? There's limited resources. There's only so much grass, or that rabbits or deer or whatever can eat, okay? And so it eventually starts to slow down and level off, okay? This is what's called logistical growth, and it's represented this way. The population is proportional. I mean, the rate of change of population with respect to time is proportional to the population, but that population is then multiplied by 1 minus p over m. Now, p is still the population, but m represents this line up here. It represents what's called the carrying capacity. Okay? So at the beginning, the population is low, and m is a constant. And so this, at the very, very beginning of a logistical growth curve, like back here, this ratio is close to 0, okay? So P over M is close to 0 over here because population is really, really low, and this M is a constant. Up here, P over M is close to 1. And now you can see what the difference between those two values does to this difference. Over here, if P over M is close to 0, then 1 minus P over M is close to 1, and this rate of change looks a whole lot like that rate of change, which is the exponential one. But as you get up here, this starts to go towards 0 because this ratio goes to 1. Okay? Now, if you're given something like this, you actually can be given it in terms of a differential equation. And I'm actually going to walk you through how to get it. And remember when I said I don't like you memorizing stuff because memorization short circuits conceptual understanding? I want you to understand how to do things. So I said memorization is bad. But I also said there's always an exception to the rule. Well, here's the exception to the rule, because this is separable, and keep in mind the whole time that k and m are constants, okay? So let's separate this. Okay, let me get that. Okay, well on the left side that looks a little bit disgusting, so let's take a brief second. Let's have a brief moment as an aside. And I'm going to change the form of this. Let's go ahead and multiply by m over m in order to get rid of the complex nature of that. Oh my gosh, that looks like the decomposition into partial fractions is going to be necessary, and it is. And I won't bore you with the actual process of decomposing it, and you can actually see, just in your mind, get the common denominator. You're going to have m minus p up here and p up here. The p's cancel out, and you're going to be back to here, okay? This is the decomposition into partial fractions of this rational expression. Well, let's go ahead and rewrite that. That winds up being 1 over p plus 1 over m minus p dp is equal to k dt. Okay, well, let's integrate that bad boy. Okay, and you're going to get natural log as a value of p minus the natural log of m minus p minus, because it's negative p down here, right? And this is going to be kt plus c. Well, I tell you what, just for giggles, let's go ahead and flip that difference. What do you say? Okay, and you'll see why here in just a second. Okay, I don't actually have to, but I'm going to. So let's go ahead and use the properties of logarithms and put that into a single logarithmic expression, kt minus c. Okay, got to start on the next sheet of paper. So let's, here, let me, okay, and let's start right there. Okay, so let's go ahead and exponentialize both sides. M minus p over p is equal to e to the negative kt minus c. Now, here's the thing. M is the carrying capacity, so it's always going to be larger than p. If that's the case, this difference up here is always positive. And of course, that denominator is positive, so you don't need the absolute value bars. That's actually a positive expression. And as I pull it out of there, I'm going to use the fact that it is it has a monomial denominator to separate the fraction and simplify p over p. I'm going to use rules of exponents here on this side to take, what was e to the negative kt times e to the negative c. We'll call that a. And here we go. Then I'm going to add 1 to both sides, 1 plus a e to the negative kt. Let's go ahead and flip that over. 1 over 1 plus a e to the negative kt. Okay, and then let's multiply by m, and that winds up giving us our formula for an exponential. Okay, and a little bit more. So here's the thing. I've shown you how to actually find that if you were so inclined. Now you're a better person for having seen it, and you don't really have to ever do it again. You just have to memorize the fact that when you are given dp dt is equal to kp 1 minus, what was it? It was p over m, right? P over m. Okay, when you're given this is the formulaic function, where a is going to be equal to the initial condition. It basically is a constant that you're going to solve for with respect to initial condition, and that carrying capacity minus the initial population over the initial population. Okay, so that shouldn't be that big of a deal. You just basically need to say, well, when I see this, I need to put it in this form with this a value, okay? And now that we've actually seen this formula and where it comes from, and I think it's always, even if you don't memorize it, it's always nice to see where it comes from so you understand why it makes sense, right? If you don't understand why it makes sense, then you're just being a method monkey, and I can't handle that. So from here, we'll go ahead and call this video quits right here. Like I said, this video is going to be largely, and now that I look at the time, exclusively conceptual, giving you an idea of what these growth curves really mean, what they're representing, why they have the form that they have, and then we can sort of move on from there, okay? So we'll do some examples, maybe 2 more videos, and I'll show you sort of ins and outs and the kind of problems that they're likely to ask you on the AP exam. Email me with any questions. Bye.